I'm here to announce Zoz. He will tell us something about data demolition. Give him applause.
Thanks a lot. Can you guys hear me okay out there? Yeah, great to be here at BaltCon. Talk is about data demolition. I'm going to throw up because you guys are a good hacker crowd. Throw up my ANSI art thanks slide for all the people that helped me with this research. A lot of people contributed to this. It took a lot of effort, and that red on black is hard to see on this monitor, but it's a bomb. At any rate, the sort of point of all this is the security risk of the waste stream. So when you throw things away, some people might be interested in those things. So those things might contain secrets that you might want to keep if you're a company from your competitors, or if you're just a normal person, you might have like identifying information, or you might have crypto keys, Bitcoin wallets, whatever you want to keep out of the hands of criminals, or just stuff that you want to keep secret from the general public, right? Not everything. Although a lot of people post a lot of things to social media, we don't necessarily want everyone to know everything about us. Back in the old days, industrial espionage, part of that, and hacking as well, was going trashing. Right? That's how the old phone freaks found phone company manuals and stuff like that, and learned how all the switches worked by going through the trash from corporations. But now, when you throw things away, the volume of data that you can toss in the trash is just exponentially increasing. Right? It's not printouts anymore. You're talking terabytes of data in something you can hold in your hand. So here are a couple of examples of that. There's great research out there on recovering old printers and copiers and pulling the hard disks out of them and just seeing what those printers and copiers have unsanitarily not deleted properly on those hard disks, right? Anything that might have been sent to the printer or photocopied that can contain all kinds of interesting information. And there's some pretty cool research white papers out there where people went and they got printers and copiers and then reported on what they found in them. Then also stuff that's mobile, stuff that's outside a fixed installation. If you've got a drone, if you work for the military, for example, or if you've got a proprietary driverless car, it's driving around with a lot of data on there that you might not want to get in the hands of competitors and stuff like that. That stuff's in the news right now. Waymo, of course, suing a person who now works for Uber for stealing all their trade secrets and taking them over to Uber. So, that's all like kind of set up motivation here, but really what this is all about is what if someone comes and tries to take your data while you're still using it? You're not throwing it away deliberately. So the goal here with this research is to, when you have a facility, whatever it is, might be data center scale, that you can flip a switch if you need to, and all your stuff is gone. No bits are left standing. And the first thing, when I talk to people about this, that they say is, well, all our stuff is encrypted. Doesn't that keep my stuff safe if someone steals my hard disk? Well, not necessarily, because crypto is only as secure as the key. So if there's a way that you don't expect that the key can be recovered from the physical media, it could be stored somewhere on that drive, or it could be recovered elsewhere. Suddenly, all your encrypted data is vulnerable if someone has access to the physical media that it's stored on. And as I said before, let's think about solutions that might be scalable up to the size of a data center. So, or a data center, right? So let's say you're running a darknet market. You've got a lot of really interesting stuff stored on there that can incriminate you, can incriminate your vendors, your customers. You might want that gone in a short amount of time under extreme circumstances. And we should assume an extremely capable adversary, right? So, let's call it a criminal adversary, someone who's going to be stealing your data while you're using it. But they should have extremely high forensic capabilities, because a threat model is always important. and security. So let's back up a little bit and see what people do what companies do, for example, when they decommission data, and if they do the right thing about getting rid of it. So when they decommission disks, the usual way to do it is you degauss the drives if they're magnetic media, and then you shred them. So you throw them into what this is, an industrial shredding machine. You can see it here taking hard disks and crushing them up into lots of little pieces. But you should, again, predict your adversary, because sufficiently motivated and sufficiently funded organizations are able to exploit drives that have been physically destroyed in certain ways. So, and as an example of that, I had a really interesting conversation with a guy who worked for an intelligence exploiting organization working in Iraq after the American invasion in 2003. And he was under instructions to recover any electronic storage medium that he found that, regardless of its physical condition, regardless of whether it had been crushed or hit with a hammer or whatever, as long as it had not also been burned, right? Because he was under instructions from NSA and CIA that they could recover interesting intelligence, potentially, from drives that had been only physically destroyed. So if you want to be super paranoid with your own stuff, you want to nuke your data from orbit, what you should do is degauss the drives, crush or shred them, burn the remains, and then spread those remains out in multiple waste disposal areas, right? That's ultimate paranoia. You'll probably be okay. But for this work, we're talking about something that happens to more data over a shorter amount of time. So here are the rules that I set for myself for doing this work. The data itself is in a server, which is 1U in height, and you get 1U above and below to put whatever you want in it, right? So that might be shielding of some sort, it might be concrete, it might be a hot gas extraction system, something like that, above and below the rack. 60 seconds from pressing the panic button to destroying everything, so that someone doesn't have a chance to stop it in progress. We want to not set off the fire systems, because we don't want to telegraph exactly what we're doing, and also that can have unintended consequences to other equipment in the facility. It might be in a co-location facility. So therefore, we also want to contain the damage to within the equipment that we own. We don't want to destroy other people's stuff and have to pay for it, and we also don't want to destroy other people that are nearby and have to deal with that situation as well. So keep that in mind when you look at my experiments here. Let's take a quick look at hard disks and what they're made out of. I'm going to concentrate on spinning platters, because when you're talking large amounts of data, that's still the most common way to store it. Platter drives, the platters themselves, are mostly historically made out of aluminum, although more commonly these days they're made out of glass. So especially laptop-sized drives, if you open your laptop drive, there's a really good probability that when you try and bend that platter, it'll actually shatter into a million pieces. I don't really concentrate on glass drives in this, because glass is really easy to smash, so it's less of a challenge. The coating on these platters is an underlayer of cobalt, nickel, and iron. The magnetic alloy itself is typically a cobalt, chromium, platinum alloy, and the layers are separated by really, really thin layers of ruthenium, so about 4 atoms thick. What this means is that hard disks are somewhat expensive to make, and they're also very chemically unreactive. So it's hard to do things like acid attacks on them. I also look a little bit about the drives that are more commonly coming into usage in things like laptops and personal computers, especially in mobile things. Solid-state drives, they're just a bunch of flash memory chips soldered to a board. So they're as physically vulnerable as any other encapsulated silicon chip that's attached to a board. So I'm going to split the methods that I looked at in this research up into 3 different varieties. Thermal attacks using heat, kinetic physical smashing, and electric attacks. And that area is where I mostly look at the SSDs. So first off, thermal. Our goal using heat to attack a hard disk is to demagnetize the magnetic media thermally. So to exceed the Curie point, that's the point at which all these aligned magnetic spins move around and get misaligned and you can't read them anymore. So for cobalt, which you find in hard disks holding those magnetic spins, that's a little bit over 1,000 Celsius. Pretty hot. Here's a few things that I didn't look at. Heating things up with a torch, and I didn't do that because some people before me did that. It turns out it's hard to heat up a hard disk from the outside with a torch very quickly because you've got a big chunk of aluminum in the case that's a heat sink. I was really excited to find some chemical reactions that didn't cause a flame that would be able to heat things up. I couldn't find any that got hot enough. And then using an oven to heat it up, and also using an inductive, basically an inductive furnace. I didn't look at that for two reasons. Firstly, they take a while to heat up, so the 60-second method makes that really tough. And secondly, it's just not that interesting. You know that eventually it's going to get to that temperature and it's going to work. So there wasn't a lot of experimentation to do there. So starting off here, the first thing I thought I'd look at was, my workshop at home. Well, what have I got that can make a lot of heat? The plasma cutter. So here we have a spinning drive, hitting it with a plasma cutter, and it's super easy. You press the switch and it goes, and it doesn't take very long. It takes about 40 seconds to complete, and it's nice. You'll see a little bit of a flame pop out the side to let you know that it's done. There it goes. In just a couple of seconds, I think. Here we go. Yep. Popping out the side. And it's sort of deceptive. This looks like not much is happening, but you're really dumping a lot of heat into that drive to make that happen. So here is opening it up. The drive stayed hot for a really long time. So actually getting the screws out, I didn't show that in the video, but I burned myself a lot of times trying to do that, and just didn't realize how hot it was going to stay. And so here's a close-up of what the disk looks like. You can see that it was spinning, but not for very long. It's mechanically seized after not too much time from probably thermal expansion in the spindle. But that plasma, goes through all the platters really nicely, and there it is, completely disassembled, and you can see we burned through all four platters in that drive. So to do this on an industrial scale, obviously you can't rely on the spinning to destroy everything on the disk. Stuff could still be exploitable on the lower platters. You would want to have an array of plasma heads, just a circular ring of them mounted above the drive. You can fit that easily into your 1U above the rack. So we could easily use that to destroy a bunch of drives in the data center and set something like that up. That's a simple engineering problem. So that is feasible. So from there, armed with that success, I thought, well, that involves a lot of energy externally to the system, but the media of these drives is aluminum. It's a very reactive metal. So what if I could use the drive itself as the fuel and just pump in an oxidizer? So my second experiment was to pump oxygen into the drive, have a little spark in there to set it off, and then just see if I could consume a bunch of the drive with pure oxygen. So you can imagine in an installation of this, you could have a little hydraulic injector nozzle that when you flip your switch, it would punch a hole in the drive and start pumping oxygen into it. So here is my setup here. I've got just a little oxygen bottle and pumping that into the drive. And we get a nice flare up, right? We're not putting much in, and the drive is burning pretty nicely. So here's some high-speed footage of that. You can see I drilled a little vent hole over the other side, so you can see the hot gases escaping, and then eventually the flames escape and everything starts to burn. Oxygen really makes things burn really well. And I actually had to stop this earlier than I wanted to. I wanted to completely destroy the whole drive, but I noticed that my hose with the oxygen was starting to melt, and I didn't want to start a dangerous fire in the workshop that could have got out of hand. So I turned everything off a little early. Here we have the drive before opening, showing that it's consumed a fair bit of the case. Opening it up, we've started to melt a lot of things inside the drive. We're chewing up the disk. If we kept pumping the oxygen in, this fire would not stop. As long as we're supplying it with oxidizer, it would keep burning, and we would eventually burn the whole drive. So here's a close-up of the disk. You can see that we've consumed all the electronics. We've burned some of the disk. So this method, I would say, also potentially feasible. As long as you keep pumping the oxidizer in, that fire is not going to go out. And the gas that's being produced is easily extractable. It's not out of control. But so now I feel like I've got two techniques that could potentially work. But when you talk to most people about hard disk destruction, and it happened to me earlier today when someone asked me, what are you going to be talking about? And I said, they're like, oh, thermite. Yep. That's what everyone suggests. That's what the military uses in their incendiary grenades, or some of their incendiary grenades. And it obviously is a way that you can destroy things with fire. What I really wanted to do was to make an injectable thermite, to make a kind of a slurry that I could mix up ahead of time, and you could have a nozzle that would just jam it into the drive, inject it, ignite it, boom. So I did a bunch of experiments with this, which I don't have time to show you today, but long story short, total failure. I couldn't gel the thermite in a way that allowed it to propagate the reaction and get as hot as it needed to get. So I had to move to other methods, but we'll get to that in a sec. First of all, for people who don't know, a little chemistry refresher about thermite. Thermite is a mixture of a metal, most commonly aluminum, and a metal oxide. In classic thermite, iron 3 oxide, red iron oxide. And what happens is those two metals swap the oxygens. So the one that's an oxide gives it up to the more reactive metal, the aluminum, and you get raw elemental iron in this mixture, plus a different oxide, and a lot of heat gets released. So you can get up to about 2,500 degrees Celsius, more than hot enough for what we need for our demagnetization. If you want to try this at home, you want 3-to-1 by weight of iron oxide to aluminum. Both of those things are really easy to find and cheap. In fact, you can get a lot of them from art supplies because iron oxide is very red. You can use it as a red pigment, and aluminum is used in silver paints. So very easy to make. You don't need particularly pyrotechnic grade materials either. You can just use just craft grade. So after my failure with the slurries, I decided to try, what if I could, I need this stuff to be inside the drive if I want to use a small amount of it. So I looked inside a 5¼ drive, and there's actually a lot of space in it. So I thought, well, I can pre-insert it, right? If we were doing this on an industrial scale, it'd take a bit of effort. You have to open all your drives and put it in there, but you can do it. And also, a lot of pins from the bus go into a drive, and some of them are not used. So you can use a couple of those pins to attach a little igniter, and then you can just wire everything up, so that's really great. And you can fit about 15 grams of thermite inside your standard drive there. It's in a little baggie. You could probably use your drives to smuggle other things to leave it up to the viewer. So here we are with 15 grams inserted into the drive, and everything's wired up, and let's take a look. So that happens very quick. We've got a lot of our 60 seconds left there. Doesn't make a big mess. We could deal with that. Let's take a look at the performance. So we can see here all of that support electronics there has been destroyed, and we've made some lumps of molten iron inside the drive. But when we start to take a closer look and clean everything off, we haven't actually done much damage to those platters. And when we clean everything off, yeah, actually not much has happened here. It's kind of lame. So that's a fail. But, you know, we're just getting started here. If you look at actually the military thermite grenades, they don't actually use straight thermite. They use a mixture called thermate. And that is a 70% thermite, 30% barium nitrate mixture. And what the barium nitrate does is it produces gas and it spreads everything around, and it also just mixes everything while it's burning. So it can actually get even hotter than your straight thermite mix. So, okay, let's give that a shot. So I mixed up some thermate. And it did its thing. Here's a high-speed shot, giving us a closer look at what's going on here. And we can see once it gets going, it's you know, it pops up the top of the drive a little bit, starts to spray out some nice sparks. You know, next time you have go camping or have a little party, you could use one of these to entertain people. But again, it kind of looks worse than it is on the camera because of the dynamic range of the camera. We could deal with this if we needed to contain it. No problem at all. A little bit messier than the plasma cutter, though. So I think we would hope for this to perform at least as well as the plasma cutter. So let's take a look inside. Made more of a mess, I think.
Actually did pretty good, huh?
Yeah, that's quite impressive compared to a straight up thermite. I guess there's a reason why the military uses this formula.
So taking a closer look at those platters there, we can see that it's produced, as we expected, a lot of molten iron, and it's spread it around much better than the regular thermite. So you can see all those beads of molten metal that are stuck on the platter. That looks good. But when we clean it off, you know, we see a few things. Number one, we've globbed some, you know, welded some molten metal onto the read write heads. We've delaminated the platter a little bit, which is great. I think that's going to mean that area of the driver is super unreadable. We've actually welded together the two platters in this drive as well with some iron. That's good. But the drive is still looking pretty decent apart from that area. You know, we can't guarantee that we've totally demagnetized that disk and we've made it resistant to some kind of exotic scanning method that an intelligence agency, for example, might have. So once again, we have to say it's a fail. But I'm not ready to give up on thermite yet, because everyone says, when you say this to people, thermite. So, all right, let's look at some other thermites, because this is not the only kind we can do. For example, we can use copper thermite. So this is aluminum as well, but instead of iron oxide, we use copper oxide. And the same thing happens, the swapping of our oxygens, and we get molten copper, which seems like it would be bad for electronics. Again, if you want to play at home, 4.4 to 1 by weight. Copper thermite is known. This was the first time I made copper thermite, actually, and it has a reputation as being a very aggressive thermite. So here's a little test pile. So it's like, you know, this is like a fireworking type of powder. So all right, cool. This feels good, right? So let's like do our little pre-insertion, put my baggie inside the drive at about 15 grams again, and let's take a look at how it goes. High-speed shot once again. So, thank you. Keep watching though. Down to the lower right, you'll see the top plate of the drive was ripped from the screws and totally blown away. So, you know, it did some damage here, but keep watching. Again, down towards the lower right there. And there is the rest of the hard disk. So that gave it enough of a whack from a standing start on a concrete block to fling it up in the air several feet, which also filled the entire workshop with toxic smoke, and we had to all flee outside and try, pursued by this evil gray-green cloud of gas. So let's taking a look inside the drive. That's the top plate, and you can see where all the screws ripped out of the corners, and it looks really cool. Nice kind of psychedelic patterns. There's the drive inside. Once again, we've covered everything, but things aren't as damaged as they were even with the regular thermite. It hasn't efficiently transferred the heat. Here's another shot looking from at the side of it. You can see even the flex cable leading to the reed heads and stuff is still intact. Looking closely at the platter itself, we've got copper spread everywhere. Actually, not just in the drive, also all over the workshop as well. And beads of copper have adhered to the inside of the case there. Maybe that is bad for the drive. Let's use our scientific cleaning technique here and see how we performed. Kind of comes right off. A lot of it, we got copper sticking to the drive there, but a lot of it didn't stick. And just because something's sticking there doesn't mean you can't clean it off again. If your adversary could just mill that off carefully or polish it off, and they might be able to read the drives again. So this method, definitely infeasible, but it was a lot of fun to do. But I'm still not ready to give up on thermite because everyone says it's the way to go. So I thought, well, what about if I build a case around the drive and I put a lot of thermite into it? So I cast a mold that was matched to the drive out of a refractory ceramic in which I could fit 250 grams of regular thermite. So there's the mold matched exactly to the drive, and it's got a foam spacer in there so that I pull that out and I've got this nice cavity that I can fill up with thermite. So here it is, just about to begin. High-speed camera footage again. Got everything clamped down to try and contain everything, and so we don't have the copper thermite problem where we had things flying all over the shop. Let's take a look. So containment, also not exactly a full success here. But once this giant cloud of flame dies down, you'll be able to see from the vent hole at the top and at the sides, almost like an oxyacetylene torch type of flame coming out of it. We're generating a lot of heat here. So hopefully this is gonna be the winner here. We're gonna really mess some shit up in this drive. Yeah, even as it's dying down, we've got that that giant white flame shooting out of the top of it. All right, let's take a look inside. So that thing looks pretty cooked. Here we are close up. So we can see again a few things. We can see that we've got some big globs of formerly molten iron that were collecting there on top of the drive. We've actually burned a hole in the top plate of the drive, and so hopefully we got some stuff inside. Sure enough, some stuff has got inside, and all the electronics is completely destroyed again. But once again, when we clean it off, things don't look so good to us. We just can't say that this is a reliable method. We can say a lot of things about it. We can say that it was fun. We can say that, you know, maybe your common garden hard disk exploiter is not going to be able to deal with it. But we can't say that the NSA is not going to be able to deal with it, right? So we just can't say we rely on it. So the moral of the story here is like, yeah, enough thermite, you can destroy just about anything, but enough might be a lot. So from here, I moved on to kinetic methods. So our goal in kinetic methods is to deform, spindle, mutilate the drive to an extent that any kind of mechanical scanning of the magnetic media would be extremely difficult to do. Because we're not demagnetizing, we need to do this in conjunction with degaussing. But that's not a problem. We can have some big electromagnets as well as doing this. The main thing is we want to do our crushing and destroying. Again, there were things that I thought about and didn't do. I didn't do any kind of hydraulic crushing or cutting. You can get systems on the market that are basically big hydraulic arbor presses that crush drives from the top. I could have made one that crushed it from the side. It just wasn't an interesting thing to do because I knew that it would work. There are a variety of high pressure cutting tools that you could use, like a water jet cutter. Again, it would work. You'd have serious engineering problems putting that into a server rack at data center scale. So I didn't bother with that. Instead, I first started out looking at projectile devices. People have said to me, you know, why don't you just shoot it with a gun? And yeah, you can shoot it hard disk with a gun, but you don't need all the things that a gun can do for this. You just want to punch a nail through it, and you can actually get a gun that fires a nail. It's called a nail gun, and they make them specifically for going into concrete. They're fired by a little .22 caliber cartridge. And so if it goes into concrete, it'll probably go into a disk drive. So here's some 480 frames per second shot of shooting the nail gun into concrete. And it all happens so fast you can't even see the nail. It goes right through. So I'm confident if it'll go through concrete, it'll go through a hard disk. So I took a drive and I carefully milled off the end so you can see the platters. And here we are hitting it with the nail gun. And sure enough, goes straight through. Bang. Nice. While I was doing this, I thought, well, the person who lent me the .22 caliber nail gun also had a pneumatic nail gun. And I said, sure, I'll give that a shot. Why not? I didn't think it would be as successful, but science is science. So here was the pneumatic nail gun at 480. And hey, color me surprised. It did great. It went straight through as well. So here's that one drive with a couple of nails punched through it. You can see that they went straight through with no problem. They bent the platters and stuck them together. Does a great job. So this is a very feasible method. It would be super easy to design a pneumatic disk system that would fit in one U, that would just push a bunch of nails through the drives. Basically, as far as mechanical is concerned, it's problem solved. Which is a little bit disappointing because I was hoping the problem would be a little harder here and that we could have some more fun with it, especially because I really wanted to do some stuff with high explosives. So I did it anyway. Now I have to just sort of qualify this. There's no doubt at all in our minds that we can destroy a hard disk with high explosive, right? So it's not interesting to just blob hard disks. In addition to smashing them, high explosives produce a lot of heat, so you get thermal factors. They do things like high explosive welding. If you get thin metal plates, you can weld them together by putting a sheet of high explosive on one side and setting it off, and it just jams the pieces of metal into one another and heats them up, and they weld together. So we get our thermal for free. But again, there's no doubt that we can do it. So my goals with this work were looking at, well, number one, okay, if we want to do high explosives, can we confine it? Because we've got these rules about keeping our stuff in the equipment. And number two, for my personal interest, can we experiment with some new techniques? And in particular, I'd been talking for years about doing explosive penetrators that were 3D printed, because I'm into 3D printing, and I thought that it was probably possible, and no one else had done it before. So, or at least no one had done it unclassified before. I don't know what they've done in the classified stuff, but in the open source literature, there was nothing. So I was like, I've been talking for years, like, yeah, we should really do this sometime. And this project was an excuse to do it. So why do you want shaped explosives? The reason is because when you set off an explosive, energy goes in all directions, and you just waste a lot because you really want to direct it in a certain way. So here's an example of that I shot this year at the Pyrotechnics Convention. Happened just a few weeks ago. And so these guys, they want to bust the rack here. This is the ground salute area, and that wooden rack, and they want to bust the rack, but they're not allowed to attach something to the rack. They have to hang it from a string. So to bust the rack, they need a really big bomb. And so they're successful. They're very happy about it, as you can hear. But look at all the energy that got wasted pointing at the ground or out to the sides, towards all those cars in the background that must have been really surprised about what was going on in that field. So there's a way that we can direct the energy from an explosive, which is called a shape charge. The technical name is the Monroe effect. And it's a little bit of a counterintuitive thing. If you have a block of high explosive and you cut a hole in it, so usually that's a conical shaped hole, but it can also be a triangular groove, that hole actually concentrates the blast. You would think that the blast would be less than that, but it actually focuses the explosive. So if you've got a thing that you want to cut through, you place the cavity against that thing. You set off your high explosive, and it actually directs the blast downwards through the cavity and cuts through the thing that you want to cut through. So it concentrates the shock wave. And you can form this very high temperature, high velocity jet, and then if you line it with a metal, you can actually form what's called an explosive formed penetrator. So it shoots this molten slug or deformed slug of metal through this thing, and that's what they use for in high explosive anti-tank rounds, for example, to punch through tank armor. So here's something from the commercial literature of a commercial shape charge, and you can see the liner. You can see the standoff, which is a gap between the explosive and the thing you want to cut through that allows the jet to form, and the penetrating jet. That metal liner has a dramatic effect on penetration with this high temperature metal jet. The metal you want has a high density and a high ductility, so typically copper is used. The military often uses tantalum as well because they have unlimited money. So here's an example of some commercial shape charges. These are oil well perforators. So when you drill an oil well, you don't want the oil to come up and get in your way initially, so you push down a sealed pipe and you finish all your well, and then when you're ready to start sucking out the oil, you send a few of these things down that punch holes in your tube and let the oil through, and then you can suck it up. So you can see the copper liner of the cone. At the top, there's a little hole for your blasting cap or your detonation cord to set them off. And some of them come with a little shield there that sets them at the appropriate standoff distance. So I managed to get a few of these from the local bomb squad in Weld County, Colorado. They're very kind to offer me some of their stuff. And here's an example of, this was actually at the end of the day when we were getting rid of some that we didn't need, but this will just give you an example, an idea of what they do. Two of them are there pointing straight upwards. And you may have seen the jets form, but here's a freeze frame, and you can see them very clearly. This is an amazing shot. You can see these, just all of that energy, basically, from the explosive being concentrated into these, almost laser beam-like jets. And this is a really interesting freeze frame. This was shot at normal speed from a regular digital camera. You can see the blast from the blasting cap that was setting these off. So we had a blasting cap going to a line of det cord, which you can see here, that was connecting the two penetrators. But that det cord, that's a hollow plastic tube that's coated on the inside with a high explosive. So it propagates a shockwave very rapidly, about 7 kilometers per second. This shot was just done at an amazing magic time where the jets had formed, but not enough time had elapsed for that plastic, that thin plastic cord, to rupture. Really an amazing shot. And that gives you an idea of just how fast this stuff happens. So here we have our unlucky hard disk with a test for one of these oil-filled perforators. And let's take a look at how it goes. You can see here the blasting cap, the det cord, the perforator, and the drive. All right, so things definitely went away here. Let's take a look at that in high speed so we can have a better idea what happened. You can see part of the drive fly off to the upper left. But, you know, things didn't go to the moon, you know, like it wasn't totally crazy. Here's half of the hard disk there, and you can see it was basically nicely sheared in half. There's the platter stack. Once again, that jet just went straight through those platters. Pretty amazing, right? Longitudinally through them. And here's all the pieces that we found of that hard disk. Obviously, we didn't find all of it. Some pieces were MIA, but you know, it did its work. But the eagle-eyed amongst you may notice something in this picture. What's that? That's the metal plate that was underneath the hard disk and a hole in it. That's the top side. That's the exit hole on the bottom side. That's the ground underneath it. And then that piece of wire above it is what we use to measure the depth of that hole in the ground underneath it. 15 inches is about, I think, 37.5 centimeters. That's a pretty deep hole, right? So this is going to present, if we were just to use these off-the-shelf perforators, we would have a blast confinement challenge. You know, even 1 U of concrete is not going to stop that. I mean, they're made for punching through armor. So here's where we get into the interesting part, where we're designing our own shape charges. So here's some just design parameters for your Monroe effect. The things that you can adjust are the apex angle of your cone, the standoff distance, and the height of the cone. 3 basic things. And here's some literature from 1965 about the velocity you get based on the cone angle. And so you see a pretty inverse linear relationship between the cone angle and the jet velocity. So that's pretty easy to tune. So I can take those 3 parameters. I want to 3D print my high explosives. So I can set up a parametric model in something like OpenSCAD that lets you write code to define 3D models. And everything's going to be great. But first we have to figure out how we're going to 3D print our high explosives. 3D printing any new material presents a big materials handling issue, right? Even if you take a normal extrusion 3D printer and you put a different type of plastic in it, you have to start adjusting things like temperature and feed rate, and you have to figure out how you're going to support overhangs, and you've got to figure out if it's important to not have internal voids, you need to figure out whether you're going to have internal voids. So that's a problem for direct 3D printing, and that was something that I just didn't have the resources to deal with, and especially, you know, you can't get high explosives in a filament, right? So I'd have to, if I wanted to use a filament printer, I'd have to make filament and so on. So I was like, well, how can I get around this somehow, but still go from a 3D design to a shape charge? So my shortcut was to print a very thin wall enclosure out of plastic, and then use a self-compacting high explosive. So a liquid explosive that would fill voids, make sure there are no bubbles in it, and I'd have the exact shape that I wanted from a 3D printer. So once again, this is the first open source literature of 3D printing of high explosives that's out there. So now I needed to get hold of a liquid high explosive. And it turns out there is one out there on the market. It's commercial, but it's expensive and I didn't want to buy it. And I'm a hacker and I want to do the hacker thing. So instead, I looked up the patents for that high explosive and I reverse engineered it and made my own. And I call it Felix, which I call Field Expedient Liquid Explosive. And chemically, it's similar to these things that you can buy in the United States that's a solid version that you don't need a license to buy. This is a really interesting thing about the United States because, as you know from the United States, they're into like a few things. So they're into freedom and they're into guns. And so without any kind of license, you can buy high explosives as long as all you're going to do with it is shoot it with a gun. These is off-the-shelf high explosive target material. So it's illegal to do anything with it except for shoot it with a gun. But if you shoot it with a gun, it's designed to explode, and it's totally legal to do this in most states. And it's a two-part binary thing. This stuff, Tannerite is one brand name, KindPak is another one, and it's ammonium nitrate and aluminum powder as a sensitizer. The one that I reverse engineered, that's a solid, so I need a liquid. Instead of the ammonium nitrate, it uses nitromethane. Nitromethane is also a really easily obtainable thing. It's used in racing fuel, it's used in model aircraft fuel. You can buy it on Amazon. And then you need your aluminum powder to sensitize it, but it has to be a special kind of aluminum powder. It's got to be coated with 1 to 2% of stearic acid. Which is just really important for the way that it diffuses into the nitromethane. So that's a little harder to get, but I got some by calling up the company, one of the companies that supplies it. Eckhart is a supplier of metal powders, and I called them up and asked for a sample, and they sent me 3 pounds of it as a sample. All of these things are easy to ship. They're just hazmat shipping, and they're not explosive until they're mixed. So you don't have to have any licenses or anything until you actually mix it up. So here's the chemical stoichiometry. What we see from this is the nitromethane decomposition. So nitromethane by itself is a high explosive. So even though you can buy it as racing fuel, it is a high explosive, but it's very, very insensitive. It's super hard to get to detonate. But it decomposes into carbon monoxide, water, hydrogen, and nitrogen gas. The aluminum sensitizes it, and it also adds energy to the reaction because that water from the nitrate methane decomposition reacts with the aluminum and produces more hydrogen gas and more heat. So you get some extra bang for your buck there. So I started off thinking about doing a ring-shaped shape charge because the things we want to destroy are ring-shaped. So I made this annular shaped charge. There's my OpenS CAD model. Here's my here's the top and bottom of the 3D prints of it. This whole thing fits with a hard disk into 1U. So I got my full 2U above and below, one each above and below for containment. You can fit about 60 grams of the Felix mixture into this annular shaped charge. And there it is, all compacted and strapped to the top of the drive with a little bit of a standoff made out of a plastic cup. And here's how it went. Not bad. That drive didn't go to the moon. Here's the high-speed shot. Or actually, rather, this is a close-up, not high-speed. This is a just a regular Canon DSLR, but in a nice protective enclosure that I made for it, so that it didn't destroy the camera. Here's another wide shot, similar charge. That one moved a little further. Once again, a close-up shot. You can see it, exit stage right there. So here's the remains, which show a few interesting things. Number one, lots of leftover aluminum. So the stoichiometric mixture is more aluminum than you need. You only need enough to sensitize it. It doesn't all react. So you're just spending money that you don't need to spend to put that much aluminum in there. As for the damage, we can see that we've stripped the platters off the spindle, and we've crushed them all together at the side there. So it's going to be pretty tough to get these apart again. But the shape charge hasn't really formed the jet. So we've cut through right in that spot, but it didn't go all the way around the disk. Why not? Well, that spot there aligns exactly with where the blasting cap was. So we formed a jet right where we initiated it, but it didn't propagate around the circle. So not really what we're looking for, so I decided to try a different geometry. This is a radial charge, so you've got all these grooves coming from the outside in, and I made a little case for the top of it as well, so that I could insert a ring of det cord at the top, and so initiate the whole thing at once from the top, and hopefully smash everything apart. The other good thing about the radial charge is you can fit more explosive in there, so you've got 100 grams here, plus my ring of 80 gram det cord, 80 grain, I'm sorry, det cord, and all taped up there. Let's take a look. All right, close up. Okay, we've got our work cut out for us here on containment, but let's see how things go. Wide shot. Yeah, so that one did kind of go to the moon. These are the bits we were able to find, so you can see that all of the components got stripped off the circuit board. The platters are pretty severely damaged. Can see that we had explosive welding of the bits that remained here. So I think it's safe to say that no one's reading this disk again. But we need to figure out how we can maybe suppress this blast. So that's the other interesting part of this research. So we want to couple the blast to the disk, right? We want to put as much of that energy as possible into the thing we want to destroy, but we don't want to direct that energy to the equipment that's surrounding it. So we want the explosive against the drive, and we want some kind of a damping material in between the explosive and the shell. So for a damping material, it would be great if we had some kind of matrix that would absorb the energy as bits compressed. So an alternating compressible and incompressible matrix that's bleeding off that energy as it goes through the material. So some kind of a foam, basically, so that the gas pockets will compress, but the things on the other side won't. We want it to be cheap, and we want to be able to inject it into the equipment when we need it, because we don't want to have our equipment full of this foam all the time, because you're going to have to replace drives as part of normal maintenance. So what kind of a magic ingredient could we use here? How about good old shaving cream? This is something I learned from an explosive engineering instructor, that when they would do punching out lock cylinders, they would use this to damp the noise and the fragmentation. So we did some tests here. So here's 41 inches of 100 grain det cord in a box filled with shaving cream, just to get an idea of what the difference is going to be. So here's the wide shot. You can see the enclosure there for the close-up camera. So already that looks a little different from the other ones that we've used. And this is actually a quite large explosion. So here are the first frames from both of our cameras of two shots that I did with that det cord. On the left is the one with the shaving cream, and on the right is without. That's the first frame from the wide camera. Here's the first frames from the close-up camera, pretty significantly different, which is reinforced by the fact that the explosion on the left has 2.5 times the explosive as the one on the right. So let's put everything together and try it all out. So here's our radial shape charge with 75 grams of Felix. Here's my 1U rack simulator. That's basically a big piece of metal with 2 angle irons of the right height welded to them, with the blasting cap in place. Then we on demand inject our foam and stick a sandbag on top of it and see how it goes. Close-up shot. Close-up high speed. So, things moved around, right? But we didn't have that giant fireball. We didn't have fragments going everywhere. The sandbag didn't survive. But if it was a concrete slab, that might have been a different story. And we can look at the piece of metal that was on top of it. In contrast to the one that we drove a giant jet of explosive through earlier, it just made a little kind of dent in it. And that's right up against. So this is on the other side of the foam, right? So, if we'd had everything just bolted down, it probably wouldn't have flown up in the air. The sides of the rack simulator did not perform as well. You can see that they just completely were folded sideways. So that would need to be a little stronger on the horizontal side. But again, the bottom steel plate, it got an imprint of the drive on it. But we fairly successfully contained that blast, I would say. If you had fully built your 3U device with some reinforced concrete on either side and on the horizontal sides, a little bit of gas extraction, I think this just might work with some engineering effort. So moving on from high explosives to electric attacks, we're in a data center. We've got electricity already plugged into things, so wouldn't it be great if we could use our existing power source against the media we want to destroy? In particular here, I'm interested in solid-state drives, because this is the way of the future when it comes to mass storage. Things that I didn't explore include using the electricity to drive a degausser. We know that works for magnetic media. I didn't look at exotic EMP microwave RF attacks. That's future work. But I looked at a few things. So part one, I thought, well, in certain kinds of detonators, they actually explode a bridge wire because you can get a high detonation velocity from basically vaporizing a wire. They use them in slapper detonators inside nuclear weapons. So I happen to have an exploding bridge wire rig, and I was like, let's try this against some flash memory chips. I didn't want to go out and buy a bunch of SSDs because they're really expensive, but they're all just flash memory chips solid onto a board. So instead, thank you to conference swag, I collected a whole bunch of free flash drives from conferences and exploded them instead. So this was courtesy of the MathWorks, great company. All hail MATLAB. So here we have exploding bridge wire rig. 2, 1. Real time. So you can see how fast that wire explodes. You're basically just dumping 15 kilovolts at an extremely high current into this wire, and it's wrapped around the flash memory chip. Oh wait, no, this is just showing you what it does. So this is nearly 1,000 frames per second, showing you how fast that happens. Pretty much instantaneous. So here we have it wrapped around a flash drive to try and couple the physical force of that explosion to the memory chip.
3, 2, 1.
High-speed shot. Wow. High speed tells you a lot of things that you don't always want to know. And in this case, it shows that it basically didn't work. The flash chip is basically undamaged. It did decap the microcontroller on the other side of the board. but the best we could say about this is it would be highly unreliable. So let's try something else. So you guys may have heard of these USB killer devices. When I did this, they hadn't done that yet, but it's basically the same thing. You have you just put a giant power spike to the electronics. You mostly want to apply the power spike to the ground line because often they'll have some kind of protection on the power line. So that's what I'm doing here. I've soldered some lead wires onto the power and ground. I'm going to raise that ground by about 15,000 volts, which it's safe to say the designer of the flash drive never expected to happen.
3, 2, 1.
See that in high speed. All right, definitely saw some things fly off there, and sure enough, when we recovered it, the lead wires have exploded within the chip. It's blasted the chip right off the board. You can see them all hanging out there. It's blasted the traces off the board. It's decapped the chip, and it split it in half. So just like the USB killer, which also works, this method is potentially feasible. Finally, this is just some eye candy mostly. I just wanted to show it to you. This is something I would love to try as future work on a metal-cased hard disk, but my rig is not big enough to do this to, but it is big enough to do it to a can. So many people have never seen this. This is inductive deformation of a metal shell. So you basically wrap a big coil around your metal thing. There's no contact, there's no electrical contact between the two, but you dump a huge amount of energy into that coil, and it makes a giant expanding magnetic field that induces a reverse magnetic field in the thing that's wrapped in it, in this case the can, and the Lorentz force does its job. The coil goes outwards, the can goes inwards. So this is some high-speed footage that I shot as part of the show Time Warp. This is 2,000 frames per second of Can Crusher. So even at 2,000 FPS, that can is cactus immediately. Here's another shot of this at 2,000. Once again, it just not only crushes, but just cuts that can in half. Non-contact. There's no physical impingement of the coil on the can. Let's take a look at this at super high speed. This is 100,000 frames per second. So this is the kind of speed that you could shoot bullet strikes in and see everything that was going on. Here on the right, another shot of that. So even at 100,000 FPS, that action takes place in just a couple of frames of video. So you can really mess some stuff up with this. So I think, if you had a big enough rig, you could do this to a hard disk, and we could do our kinetic attack with electricity, but the necessary power levels, currently unknown. A subject for future research. So quick summary of the three methods. Most feasible methods in thermal with a plasma cutter and the oxygen injection. So sometimes low tech is the best. You may have to design an injector. In kinetic, the nail guns work great. Know your adversary. You may not want to just nail gun your hard disks. The damned high explosive also could totally work, but you'll need to set up your barrier not just above and below, but also around the sides. And on the electric attack, high voltage power spike works great. There's still a lot of work to be done on SSD forensics resistance, though. So, if you're storing your sensitive information on SSDs, you may not want to rely on this method until you know more about SSD forensics. I just want to close out, even though I know I'm just a couple of minutes over here, with a thought experiment on mobile solutions. Does anyone know who these guys are? On the left is Ross Ulbricht. He ran the Silk Road. On the right is Alexandra Kazis. He ran Alpha Bay. And what they both have in common, as well as apart from running at the time the world's biggest darknet drugs markets, was they both got busted, and they both got busted with their devices unlocked. So they were captured, and their systems were running and unlocked, and so their encryption made no difference whatsoever to the outcome of the situation. Ulbricht is in jail. Kazis is dead in a Thai prison. So bad news. So if you're running a darknet market or any other thing where you think people might be coming after you for your data, you might want to consider having some kind of proximity-based dead man switch along the lines of this. It turns out you don't need much to blow up a laptop either. That was about this much det cord inside the laptop. So I'm happy to take questions, although I don't want to run into the next guy's time here. So maybe I'll leave it to the organizers here if they want to do questions now or afterwards.
3 questions. We have time for 3 questions.
When it comes to direct charge, can you do something opposite on the upside to reduce impact to stuff above?
Yeah. So you mean like directing some energy in the opposite direction to try and like balance it out?
Actually, I think doing what's it called? This kind of shape on the upside of the charge.
Yeah, I did a couple of other experiments with some very, very flat charges that you initiate from both sides, and the idea is you direct a bunch of energy downwards and you balance it with some to the top, but they weren't successful, so I didn't include them. But maybe. I mean, like I think there's a lot of room for experimentation with being able to, just like 3D printing, anything else, being able to 3D print your geometries means that you can easily do a lot of tests. And I certainly aim to do more experimentation at some point.
With your thermal methods, did you actually measure whether you had reached Curie temperature or not? Or did you just look at the result and determine that it wasn't?
I just looked at the result because it was pretty clear to me just from watching what had happened that even if the local temperature in the reaction was, a couple of hundred degrees, a couple of thousand degrees, that if it hadn't propagated to any like visible deformation on the disk, I just know how effective the heatsink is on the drive. So I just, it's possible it might have worked better than it looked, but I wouldn't rely on it. So because the bottom of the hard disk is just a giant heatsink. And you can see that if you do put a temperature probe inside a drive and heat it with a torch, which other people have done, it takes a really long time for that heat to get over the other side.
Have you ever tried going the other way, for example, using liquid nitrogen and trying to break apart the disk after that?
Yeah, someone asked me that recently as well, and I have not, but I have used liquid nitrogen a lot of times, and I haven't noticed. Like, I'm really skeptical about the whole metal becoming very brittle when you put it in liquid nitrogen. Like, people say you can freeze a lock and you can break it. It's one of those things until I do it myself, I just don't believe it, and I haven't tried that myself, but I've put liquid nitrogen in metal containers a lot and I've never had one break. So I just feel like, metal just doesn't get that much more brittle than it already is. Even at a low temperature. It's my feeling, and I don't have empirical evidence to back that up. And I think enough people have asked me that question now that I'm going to have to go and try it for myself, which is going to be great because liquid nitrogen is easy to get. But yeah, my feeling is it probably doesn't affect things that much.
I'm sorry we don't have time for
But
any more
Ask me
questions.
anything for
You
the rest
can-
of the weekend. I'll be here. So thank you.